Take the integral from negative infinity to infinity of sine x over x. The answer is pi. Now multiply by sine of x over 3 divided by x over 3. Integrate again, still pi. Add sine of x over 5 divided by x over 5. Still pi. Keep going. 7 factors. 7 times the answer is pi. Then you add the 8th factor, and the answer is not pi. It is pi minus something extraordinarily small. The pattern breaks. Before we understand why it breaks, we need to define what we are computing. The sinc function is defined as sine of x divided by x. It equals 1 at x equals 0 and oscillates towards 0 as x grows. It is one of the most important functions in signal processing. Its integral over the entire real line equals pi. This is our starting point. Now we multiply sinc functions together. Start with sinc of x. Its integral is pi. Multiply by sinc of x over 3. The product still integrates to pi. Multiply by sinc of x over 5. Still pi. Multiply by sinc of ax over 7. Pi. Sinc of ax over 9. Pi. Sinc of x over 11. Pi. Sinc of ax over 13. Still, exactly pi. That is 7 integrals in a row, all equal to pi. The pattern seems bulletproof. Why would it ever stop? Now multiply by sinc of x over 15. Integrate, the answer is not pi. It differs from pi after the 50th decimal place. The difference is approximately 4.6 times 10 to the negative 11th. Almost pi. Unimaginably close, but not pi. To understand why this happens, we need the Fourier transform. The Fourier transform of the sinc function is a rectangle. Specifically, the transform of sinc of ax is a rectangular pulse of width 2a and height pi over a, centered at the origin. When we multiply sinc functions in the time domain, we convolve their Fourier transforms in the frequency domain. The integral we are computing is the value of the convolved result evaluated at 0. Start with the rectangle for sinc of x. It has width 2, height pi. Convolve with the rectangle for sinc of x over 3, width 2/3. The result is a trapezoid. Its value at 0 is still pi. Convolve with the next rectangle, width 2/5. The top of the trapezoid narrows slightly, but the value at 0 remains pi. Each convolution shaves the edges, but the center holds. The flat top of the convolved shape stays at pi, as long as there is still a flat top. Here is the key. The flat top survives as long as the sum of the half-widths of all the rectangles except the first is less than or equal to the half-width of the first rectangle. The first rectangle has half-width 1. The remaining half-widths are 1/3 plus 1/5 plus 1/7 plus 1/9 plus 1/11 plus 1/13. That sum equals 0.95555, less than 1. The flat top survives. But add 1/15. The sum becomes 0.95555 plus 1/15, which equals 1.0222. Greater than 1, the flat top vanishes. The value at 0 dips below pi. This is the precise moment the pattern breaks. Not because the mathematics changed, but because a running sum crossed a threshold. The deficit can be computed exactly. When the sum exceeds 1 by a small amount epsilon, the value at 0 decreases by an amount proportional to epsilon. For the case with factors through 15, the deficit is approximately 4.6 times 10 to the negative 11th, a tiny number, almost pi, but not pi. This is not a coincidence specific to odd numbers. Borwein and Borwein showed that any sequence of positive numbers will produce the same pattern. The product of sinc functions with these parameters integrates to pi as long as the sum of all parameters except the first is less than the first parameter. The moment the sum exceeds that threshold, the integral drops below pi. The pattern is universal. What makes this result extraordinary is not the break itself, it is the seduction. 7 consecutive equalities create a psychological certainty. You stop checking. You assume the pattern holds forever. But mathematics does not care about your assumptions. A pattern is not a proof. 7 instances of pi is not a theorem. And this particular integral reminds us, with devastating precision, that the line between pattern and truth is thinner than 10 to the minus 11. An integral, a product of sinc functions. Pi, 7 times in a row, then not pi. The explanation lives in Fourier space, where rectangles convolve and a flat top gradually erodes. The moment the edges spill past the boundary, pi is lost. Not by much, but lost. Sometimes the most dangerous thing in mathematics is a pattern that almost works.